Let me start. So I think last time I did derive this equation, which is 1 half m v rho squared is equal to E minus the effective potential of rho. Is everybody aware of this? All right. So what do? We have this equation, and U effective of rho was defined as U effective of rho was defined as the U of rho, which is the potential due to the central force. Okay, potential due to the central force. And then we had another term which was L squared by twice m rho squared. And this term we recognized as the potential due to the centrifugal force. The potential due to the centrifugal force. Okay. And next, I believe, did I do any problems involving gravitation? Okay. Have I solved the general problem of motion? That has been done. So then let me move on to the gravitational field. So the starting point is of course the Newton's law of gravitation, which says that if I have a massive object m and another object m, such that the position vector of this m is r vector, and I'm going to define a unit vector r cap. So then I'm going to find that f vector is equal to g m times m divided by r squared times r hat with a minus sign. So you can see that this is indeed of the form f of r hat, which is the definition of a central force. So the gravitational force is a central force. Okay? So where my f of r is equal to minus gmm divided by r squared. Okay? There is a minus sign here which tells you that the force is attractive. Okay? So f of r is equal to this, and remember we can define the potential due to this force for a central force as minus du of r by dr. Okay, so what do we get then? So I'm going to find that du by dr is equal to gmm by r squared. But this can be written as minus d by dr of gmm divided by r, because the derivative of 1 by r is minus 1 by r squared. That kills that minus sign. So I can write du by dr is going to be equal to d by dr of minus gmm divided by r. So if I now equate u with whatever is in the parenthesis here, I'm going to get an expression for u. So u is equal to minus gmm divided by r, and this is the potential, the gravitational potential due to the mass m. The gravitational potential energy, okay, acting on mass m. This is the gravitational potential energy of what object? It's usually of the object that experiences the force. So we are interested, so U is equal to the gravitational potential energy of the mass m. Okay, the small mass m. The capital mass M is held fixed. So this is the center or the source of the force. So that is held fixed and is sort of out of the consideration here because it doesn't move at all. Okay. So this is what we get. So let us then try to write down the expression for the effective potential. So U effective of R now, I'm using R in place of rho. Okay, and that can be written as, what is it now? The gravitational potential force is minus GMM divided by R, plus I should have L squared by twice MR squared. Is that right? And so remember, sometimes people use K is equal to GMM. This is a constant, of course. So therefore, this can be written as minus K by R plus L squared by twice MR squared. So then what is my equation if I substitute it into the radial equation of motion? I'm going to get 1/2 m into VR squared, the radial velocity squared, can be written as E minus U effective, that is minus K by R plus L squared by twice MR squared. So this is the equation that we have. Okay. So now let me try to plot U effective of R. So if I plot U effective of R, there are two terms here, right? So let us say this is my R. So this minus K by R is a negative potential. Right? So therefore it has its existence entirely below the x-axis. Right? So this can be the energy axis. Okay, so this is entirely below. So let me write down, let me show how that looks. That has a negative infinity at R is equal to 0. So I'm going to have negative infinity and it slowly approaches the horizontal axis, right? Because as R tends to infinity, this tends to 0. But at all times it stays below that horizontal axis. What about the other term, the second term? The second term has a 1 by R square. So at very small distances, it is a very large positive number. At R is equal to 0, it is plus infinity. So the y-axis is actually the asymptotes of these two curves. So I'm going to have a large value, but then because it has a 1 by R squared, it drops very fast to 0 as R goes to infinity. So therefore it starts large and it drops. There we go, something like that. Okay, so now what I'm interested in is the sum of these two curves. So when this is large and positive, this is not as much negative. So therefore I'm going to have a net positive contribution, and let me draw that contribution here. So that contribution is going to be positive, but eventually it's going to come down, it's going to cross over, and then it's going to turn up because the positive part is getting smaller and smaller, and then eventually it's going to try to follow this curve, right? It will approach 0. So it never crosses the horizontal axis after this dip. So there is going to be a dip over here, so it's going to come down, and this is going to infinity as R goes to 0. Is that right? So let's try to remember the black curve very carefully. Okay, so let's try to see what kind of trajectories we are going to get for different possible values of the energy. So let's do that. So let me first take E is greater than 0. So I'm going to draw this curve again, and I'm not going to draw the other two curves. I'm only interested in this curve. And let us say this is my energy axis, of course. So I'm going to have a positive energy. So this is E is greater than 0. Okay. And now let us see what happens. It's going to intersect this curve at this point. So let me draw a vertical line. corresponding to that. So that line is going to intersect the R axis over here. So what happens in this region? In this region, the potential is larger than the total energy. So what does that mean? The potential is larger than the total energy. So this shaded region is called the forbidden region. Why is it forbidden region? Because in this region, the energy is less than the potential. Right? So that means I'm going to have 1/2 m VR squared is less than 0. Is that possible? Because then VR squared would have to be negative and VR would have to be pure imaginary. That's why this region is forbidden. And what happens at this intersection point? We call this intersection point as the turning point. It is called the classical turning point. So that means the particle can come here, okay, and then it has to go back. It cannot go further in because that will be a forbidden region. Is that right? So how does the actual trajectory look for this particular case? So let us say here is the center of the force, right? So what happens is here I'm going to have this planet or particle that is being projected here with E greater than 0, and of course L is also greater than 0. So then what happens? It goes like that and comes like that. Of course, the sun has to be placed a bit more symmetrically here. I'll do that now. So the thing is somewhere over here. And this is a smooth curve. Oh gosh. I don't know why it destroys the whole thing. Still not so good, but that's all right. So this is to be a smooth curve, right? There is a smooth curve. Okay, so you can see that there is a distance of closest approach for this. Let me call that as RC. How do we find RC? Well, we know that at the turning point, you must always remember this, at the turning point, RC, let us say, or this point P here, so that if this is the origin, then I know that OP is equal to RC. Then at the turning point P, what happens? VR is equal to 0. Because the radius of this is not increasing. The angle is changing. So notice that VR is equal to 0, but V vector is not equal to 0. The particle is not at rest there. The particle has a motion in the tangential direction, right? But the radial direction velocity is 0. Okay. A simple example is if I throw a chalk, what's going to happen? It's going to go to a topmost point and stop and come back. So the velocity along the y direction is 0 at some point. But if I have a projectile motion, I throw a body like this, then what happens at the topmost point, the Vy component of the velocity will be 0. But the Vx will remain. Is that right? So that is the kind of situation we have over here. So then what happens? Let me try to find out. I'm going to find that E, so therefore, my apologies. So therefore I should have 1/2 m VR squared, which has to be 0, is equal to E minus U effective of R. So therefore, I must have E is equal to U effective of R. So the root of this equation will give the turning points, will give the location of turning points. Is that right? So let's then try to use that fact. So I'm going to find that U effective of R, we've already found out, is equal to minus K by R plus L squared by twice M R squared, and that has to be equal to E. So let us put u is equal to 1 by r so that this becomes a quadratic equation in u. So I am left with L squared by twice mu squared minus ku minus E is equal to 0. So let us try it. This is a quadratic equation. I can find the roots. So I'm going to find that u is equal to, what do I get? I'm going to get a k plus minus square root of k squared. There is a minus sign here, so this becomes a plus sign. I'm going to get a 4 times E times, I'm going to get L squared by twice m divided by twice the coefficient of u squared, which is going to be L squared by m. So I can write u is equal to m times k divided by L squared, and I've taken the k common here. I get 1 plus minus square root of 1 plus, this 2 cancels with the 2 with the 4 here. I'll get a 2 here. So I'm going to get twice E times L squared by m into k squared. This is the root. Can I have a negative sign here? Sorry, a negative sign here? I can. Oh, no, I cannot. Why is that? Because this quantity is larger than 1. So 1 minus a quantity larger than 1 will be negative. Is that right? So therefore, only one root is possible. The other root is negative, which cannot be allowed. So only one root is accepted. And what is that root? So this, by the way, is equal to 1 by r. So therefore the RC is equal to the reverse of this, that becomes L squared by mk, and I'm going to have a 1 by, I should have a 1 plus square root of 1 plus twice EL squared by m into k squared. So this is the location of the distance of closest approach for this particular thing. This trajectory here is a hyperbola, and it is an unbounded trajectory. That means it comes once close to the center of attraction, and then it goes away and it never comes back. It's gone. Okay? All right. Let us try to take a look at another situation then. So let us take a look at another situation then. I'm going to have, let us say, this is going to be my effective potential again. So mind you, all of these things are done basically from the energy diagrams. So energy diagrams are a very powerful tool, right, that can help you solve a variety of problems. So now what happens? I've already considered the case of positive energy. Let us lower the energy a little bit. So let me take the energy to be exactly along this horizontal line. So that means my E is equal to 0. So what happens when E is equal to 0? Well, so I'm going to have again one turning point. So this is going to be my turning point. And I'm going to have a forbidden region. Okay, and let me choose a different color here. Okay, so this is the forbidden region. Is that okay? Can you see that? Just barely, I think. Maybe I should choose this. So that is the forbidden region. Oh gosh, the whole thing left. So there, it's back, doesn't matter. So now this distance over here from the origin will be my distance of closest approach. So how do we find the distance of closest approach? Again, mind you, the turning points are always given by U effective of R, and this we are told is equal to 0. So I'm going to have a minus k by r plus L squared by twice m r squared is equal to 0. So I can immediately read out one root. No calculations required. Yes, speak up. I think you have the right answer. Let's hear it. Infinity, exactly. So r is equal to infinity is one of the roots. So let's now exclude that root. So then I'm going to get minus k plus L squared by twice mr is equal to 0. So that will give me the other root, which I'm going to call as RC. So I'm going to get k times twice m divided by L squared is equal to 1 by RC, and that is equal to twice mk by L squared, which means that RC is equal to L squared by twice mk. Okay. Let us take a look at the previous formula. It's right over here. Oh. It's right over here. Say that again. Where is the root in the denominator? Here. That's right. So that's precisely what I'm trying to say. If I put E is equal to 0 in this equation, in the outlined equation, what do I get? So I'm going to get RC for E is equal to 0. What do I get? I'm going to get L squared by mk times 1 by, there is a 1 here plus a 1 here. So that is equal to L squared by twice mk, which is the same answer that we got over here. Is that okay? Why do I take? Because I'm interested in this problem, E is equal to 0. And the turning points are given by E is equal to U effective of R. Okay. Alright, now let us see what happens when E is less than 0. Okay, so I'm interested in, let us say, this fellow. So let us say I'm interested, let me redraw the graph, or I can, yeah, redraw the graph. So here it is. I'm going to have the effective potential that looks like that. And I'm interested in, let us say, E is less than 0. So now there are two turning points. Let me call that as R1 and this as R2. Is that okay? So how do I find, and you can see that R1 is smaller than R2. And you can see that the particle is completely confined in this region only. It cannot go here because that is forbidden. It cannot go here because that is forbidden too. So both of these regions are forbidden. So if I draw a vertical line over here and a vertical line over here, okay, then this region is forbidden and all of this region is forbidden. So the particle is only confined to this small region, to this region. Yeah, question. Yes, what will be in the oh yeah, that's a very good question. Let me answer that question. So that means the path here, what is the trajectory? The question is asking is what is the trajectory in this case? The trajectory is going to be somewhat similar to what we found in the earlier case. It's again going, whoops, what am I doing here? Okay, it's again going to be a center, and the particle comes like this and goes away like that. So again, this is an unbound orbit because the other point is at infinity. So the object will have to go to infinity, right? So this is the closest distance, which is RC, but the shape of this trajectory is that of a parabola. okay, is that of a parabola. Whereas earlier, if you remember, we had, what happened? Earlier we had a hyperbola. Okay, so now this becomes a parabola. So now let us see what happens when E is less than 0. When E is less than 0, there are two turning points. So let us try to see what happens. So I'm going to write E as equal to minus of the modulus of E. Right? The modulus only takes the magnitude, and because it is negative, I'm going to put the negative sign explicitly. And then again I'm going to have E is equal to U effective of R. So that means I'm going to get minus of the modulus of E is going to be equal to minus KU plus L squared by twice M into U squared, where U is equal to 1 by R. Is that right? Let's try to see what kind of a quadratic equation I get in this case.
Yeah,
Huh?
you can just write the answer for RC, the value above to calculate it using the quadratic formula.
I write the answer.
The first case in which you did the calculation,
Yes.
it's the same thing.
It's not the
Addition
same.
of E, you can put minus E plus minus.
Well, let's do that. What's the hurry? So what do I get then? He's somewhat right. He's saying that you'll get a similar quadratic equation. Question. That you determine by actually solving the equation of motion, which we are not doing right now. Right. So that does require quite a bit of calculus. And it's done in the book, by the way. Right. But we are not going to ask you to do the full integration. Especially if you have the radial equation, you can carry out one integration even without knowing what the shape of the force is. And that equation is, if I do that integration, I'm going to get this equation. This equation. So this is what is called as the first integral of the integration of the radial equation. This much you can do. Beyond this becomes difficult, because the integrals themselves can involve what may be called as transcendental functions. For the case of the inverse square law, it turns out it is given in terms of sine and cosine, but it requires several substitutions for you to be able to do that. So that's a fairly tall mathematical issue, so which is excluded in the syllabus for this semester. Okay? But if you are interested, you can certainly read the book. The book has the details. Okay. All right, let's take a look at the quadratic equation that we get over here. So I'm going to get L squared by twice M U squared minus KU. I'm going to get a plus of modulus of E, and that's equal to 0. So again, I'm going to get U is equal to, what do I get here? I'm going to get K plus minus square root of K squared. And now I'm going to get a minus sign, because both the coefficient of U squared and this constant here is going to be positive. So there will be a minus sign here, and this I think is going to be equal to twice L squared by M and a modulus of E. Okay, and I have to divide this by L squared by M, which can be written as M by, I'm going to take MK by L squared into square root of, okay, MK by L squared into 1 plus minus square root of 1 minus, I'm going to get twice L squared modulus of E by M into K squared. That's what I'm going to get. So now two roots are possible because there is a minus sign in the square root. So whether I add, if I take the plus sign, I certainly am going to get a positive value. If I take the negative sign, I'm also going to get a positive value, because the quantity in the square root is going to be less than 1. Is that right? So therefore I'm going to get two roots, and the two roots are the reciprocals of this. So I'm going to get R1 is going to be equal to L squared by mk, and let me call this square root quantity as alpha. L squared by 1 plus alpha, right? And R2 is equal to L squared by mk into 1 minus alpha, where alpha is equal to square root of 1 minus twice L squared modulus of E by m into k squared. Is that okay? Good. Now we have got something very interesting. So we know that the trajectory here is an ellipse, right? And the planet is at the focus. So the distance of closest approach is going to be your R1, and the distance of furthest approach is R2. Okay, so both are finite quantities. And if I look at this entire distance over here, which is R1 plus R2, that is called twice A, where A is called the semi-major axis. Is that okay? So let us then try to find what is twice A. Twice A is equal to R1 plus R2, right? R1 plus R2. So notice that the way I've written it, R1 is less than R2. So I'm going to get, so that is equal to L squared by mk times 1 plus alpha plus 1 minus alpha. So that is equal to L squared by mk times I get 1 minus alpha squared times I get 1 minus alpha plus 1 plus alpha. I have taken the lowest common denominator. Okay, so the alphas cancel out over here. I get a 2. So this becomes twice L squared by mk into 1 minus alpha squared. Let's try to calculate what this quantity is. 1 minus alpha squared is equal to 1 minus the square of that, which is 1 minus twice L squared modulus of E divided by m into k squared. So I'll open the bracket, I get 1 minus 1 plus twice L squared E divided by mk squared, and the ones cancel out. So this is just twice L squared. Oh, I should put a modulus of E here. Modulus of E divided by mk squared. So let me substitute this over here. So this becomes twice L squared by mk times the inverse of that. So that becomes m times k squared divided by twice of L squared times modulus of E. So I can cancel this 2 and L squared and 2 and L squared. So what happens, I can also cancel this m, cancel one of the powers of k. What do I get? I'm left with 1k there divided by, I think there is a modulus of E, is that right? Anything else left there? Not that I know of, okay? So this is equal to 2a. So therefore a is half of that, so it is k divided by twice of modulus of E. What is the surprising thing here? The surprising thing is that the semi-major axis is independent of the angular momentum. It only depends upon the energy. Is that right? Okay, so we have negative E. Now let's go further down. We want to reduce the E some more. Okay, so let me draw that. I'm going to go like this and like that. And now what is the smallest value of the energy that I can have? The most negative energy, the one that is tangent to this, right? Can I have any energies below this? No, because then the entire R axis is going to be forbidden. Because everywhere along the points along the R axis, I'm going to have potential energy is larger than the total energy. That can never happen. Is that right? So therefore, there is going to be only one point of contact, that is R. And this point of contact, what happens? You can imagine what happens as I slide this down. So as I slide it down, what happens? The two roots start to coalesce, right? So we are looking for the condition when R1 equals R2. So let us try to see what are R1 and R2. We know what they are. R1 is equal to L squared by mk into 1 by 1 plus alpha. Am I right? Yes. And that should be equal to L squared by mk into 1 by 1 minus alpha. So when can these two be equal? Alpha should be 0. So you get alpha is equal to 0. So what does that mean? That means that the common radius r, I'm going to call it r0 or some people call it r, is going to be given by, what is that? L squared by mk. That much is known. What is the value of the energy at which this happens? Remember, the condition is alpha is equal to 0. And what was alpha? Alpha was given by this quantity here, 1 minus twice L squared modulus of E divided by M into K squared, and that must be 0. So I can find a relation between E and L for which this has to be true. So therefore I am going to find that modulus of E is going to be equal to 1/2 into mk squared by L squared. So the relation between E and L is in this fashion. Okay, I can go back and substitute the expression for E, which is equal to minus k by r plus L squared by twice m r squared, and substitute this value for r. That will also give me the total energy. Okay, I am sure you are going to get the same thing. So the energy, by the way, is equal to minus of modulus of E. So what we are determining here are the modulus of energies. So from this you can find out what is the total energy. The radius, yes, exactly, because both the terms are equal. So this is equal to A for a circle. So this is clearly a circular orbit. Okay, so let me pose as some exercises for you people. Okay, the exercises are: find the time period of the orbit in which I am going to have energy E and L such that E is less than 0 and orbit is circular. Okay, so that would be a good exercise for you to try. We can also now look at issues involving perturbation of orbits. So we know that if I know E and L, I can determine a lot of things as far as the orbit is concerned and so on. Is that right? So how do I calculate what happens if I somehow change that orbit? Supposing I'm going to have a satellite or a planet that is going around in a circle about some massive object M. This has a mass M. And let us suppose I'm going to have some asteroid or something that provides an impulse J to this planet such that the direction of the impulse passes through the center of the circle. Okay. Then what happens as a result of this impulse? So what happens when J passes through the center of the circle? There will be no change in angular momentum. Right, there will be no change in angular momentum, but what will change? Energy will have to change. It's oh, because I am wrong. I am wrong, that's why. So what happens here? So here I am going to have a velocity J by M, and there is going to be a tangential velocity, right? V theta. So initially the energy was E. Okay, and in a circle VR is 0. Right. So the initial energy is equal to half m into V theta squared. Is that right? Essentially that is, okay, wait a minute. So that is really nothing but just oh, I'm in a hurry, I do all kinds of crazy things. So this is really L squared by twice mr squared. Right? That is the initial kinetic energy. And from that I can find what V theta is. Okay, so I'm going to find that the new energy after the impulse is going to be equal to the square of this plus the square of that. So that's going to be equal to 1 half m into V theta squared plus j by, j by m squared, because these are in perpendicular directions. But this is the initial energy. So this is going to be equal to the initial energy plus the final energy becomes j squared by twice m. So now I know the final energy, angular momentum L final is equal to L initial. So I know the final energy and the final angular momentum. I can find the trajectory. Yeah, so this is what I'm going to get. So I can find the initial, compare the initial energy with the final energy and find the final energy. And I know that the angular momentum has not changed. So now I know EF and Li, and that is equal to LF. So once I know EF and LF, I can find what is the new trajectory. Yeah. Say that again. Say that again. No, at the instant of collision. Okay. At the instant of collision, I know what the final energy is. Right? And that energy is conserved. After the impulse, whatever energy I have, energy has changed obviously. But the changed energy remains constant. Okay, good. So now let us see what happens if I have something in a circular orbit, and let us say this is a satellite and it fires a rocket so that J is in the direction of its tangential motion. Then what happens? Angular momentum will change. So LF is going to be equal to L initial plus or minus depending upon the direction of J. If the particle is moving in this direction and J is in the same direction, so then this becomes equal to, what is it? J divided by J times R, the radius of this, right? That's it, J times R. Ooh. So it's going to be J times R. So R is equal to radius of the circular orbit. Okay, what happens to the energy? So that is going to be equal to, what happens? The tangential velocity is now going to be equal to the initial tangential velocity is equal to the tangential velocity initial plus, I'm going to get a J divided by M. Is that right? So what is the total energy then? E final is going to be equal to 1 half m into the tangential initial thing plus J by m whole squared. So I can calculate EF and I know LF, and again I find out what kind of trajectory I can get. Mass will not change. Why should it change? No, that thing doesn't stick to it. It simply, it's like hitting a hammer and the hammer is not sticking to that thing. Oh yeah, I mean, you can assume that that change in mass is negligible. Okay. Somehow some impulse is provided without appreciable change in the mass. Okay. So these are some things you can solve for perturbation of orbits. I think I'm done today. Any questions?